Hey. Well, good morning. Okay. So, can you hear me there online?
Yes, we can hear you.
Okay. So we're going to continue our discussion of the Kondo impurity model first, and then apply it to Kondo lattice models, which I'll describe shortly. But the model we're considering now is electrons, it's the C electrons, which are moving on some lattice at some finite density. So there's a metallic state here of the C electrons. This is meant to be a 2 or 3 dimensional lattice, despite the nature of the picture. And then there's a single impurity spin, which is coupled to these conduction electrons by the Kondo coupling JK. And it's coupled to the conduction electrons on the site 0, which is the origin right here. Okay. And I've written this in a form which will generalize to models with SUM symmetry. We're interested, of course, in the case m equals 2. But there's a large M theory which is actually quite powerful, which I'm going to describe today. All right, but before I begin that description, any questions? All right, so what we saw last time was kind of a historical overview of the observations and the normalization group analysis of the Kondo effect, and it led to many wonderful developments in other fields of physics too. And historically, it was quite important in developing all the technology. But somewhat surprisingly, actually, much of the physics of the Kondo model can be quite well understood by a theory which, as we'll see now, is not much more than a glorified Hartree-Fock theory. And there were people who did this in the early days, Varma and Yaphet in particular. But it took some time to understand that this theory really made sense and wasn't as silly as it looks initially. The big stumbling block was something we've already encountered, is how do you talk about spins in a way that's involves free particles, and we've learned the parton method and applied it to spin liquids, and really the parton method also works really well here, as we're going to now discuss. So we take the spin and represent it in terms of some partons F, which are sometimes called spin-ons. We started with the d electrons in the d band, and these are effectively the same eventually. But just to remember that there's a constraint on these fermions, and when I used a different symbol for them, F rather than D. Okay. So I'll call them spin-ons. Okay. So then you do a large M theory, and I outlined the Hubble trigonometric root to it last time, but let me just write down the final answer, which is actually quite easy to guess. So in the large M limit, we're not going to look at 1/m fluctuation mostly today. All you have to do is just take the interaction term and do a factorization of it. So the conduction electrons go along as before. This term you factorize, and the usual trick, the first thing we learn in the course, when you have operators like this, you can write them as A dagger D, times B dagger C, and so on. So if you just do that here, and in fact only factorize in the F dagger C channel, and that's what the large M limit tells you, since they have a common alpha index, that's the most important channel to factorize in. So you factorize this and you get that, and if you take the expectation value of this and you get that, which are these two terms here, and this coefficient P bar has to be determined self-consistently from the mean field Hamiltonian. And finally, you also have to impose this constraint. And I guess this was the mental leap that was hard to take early on, that you could just impose this constraint in a mean field way. But it becomes more and more accurate as n becomes large. And actually, it's not so bad even for m equals 2, as we see. So you introduce a Lagrange multiplier lambda bar, and this has to be adjusted so that this is satisfied. Okay. So the problem is very simple, really, surprisingly simple. Here's a free fermion Hamiltonian with two parameters, lambda bar and p bar, and you determine those two parameters by solving these equations self-consistently. So now I'm just going to go through the mechanics of how that's solved. Nothing deeper than that. And we'll see we get actually much of the physics of the Kondo effect just from that calculation. And it's very instructive how it appears. All right, so first, let's just take the mean field Hamiltonian and think about it a little bit. This is sometimes called, has a life of its own. It's sometimes called the resonant level model. Of course, this is in the context where all the parameters are just numbers not to be determined self-consistently. The only thing the Kondo model will add is the self-consistency conditions. So in the resonant level model, you have some, if I plot the density of states of the conduction electrons, well, the conduction electron has some, well, I don't know, not semicircular, but some density of states. And here, D of E is the local density of states. So for the conduction electrons, D of E would be sum on K, delta of E minus EK. We look at all the single particle states which have energy EK, and then depending on your band structure, you get some density of states. So this would be the density of states that you're going to measure, say, at the origin. It's the same on every site because the conduction electrons are translationally invariant. So that's the density of states of the conduction electron in some continuum. And then you have a resonant level. You have a singles level. So that initially would be a delta function. And you can see from this that the answer now depends very much on where the energy of that level is. So if lambda bar is over here, down here, then, this state is a localized state. It's just sitting on the site 0. And these are extended states, plane wave states that extend to the whole lattice. But if it's not in the regime, if that energy there are no extended state, this state is going to remain localized. It will be exponentially localized. It will remain a delta function. Its energy may shift a little bit, but it will be some bound state of the impurity, which is totally localized. And similarly over here, but the case we're interested in is when the resonant level is somewhere in the middle of the band, maybe even at the Fermi level. So there's a resonant level here. This is lambda bar. This is at p bar equal to 0. And what we now show quite simply is that when you couple these two together with p bar, this is going to become a Lorentzian. And of great interest to us would be the width of this Lorentzian. So basically, you have a local level which is going to couple the continuum, and the local density of states near the impurity will show a resonance. Okay. Well, that's really easy to compute here. This is just a problem in scattering theory. We can do it quite simply by Green's functions. So for example, if I want to compute the Green's function of the F spin-ons, that's the bare Green's function plus, so this is an F particle, then it goes to a C, which goes to an F, and this is just P bar, and so on. Very easy to work out. C. You get F, C, F, C, F, and so on. And so this will be, you can sum this with the Dyson series, and it's easy to see. It's omega minus lambda bar. That's the imaginary frequencies. I omega minus lambda bar, that's the bare Green's function. And then there's a self-energy here, which is going to be, make sure I get the sign right. But I can just guess, I don't think I need a P bar squared. You'll get a sum over 1 over volume, sum on K, 1 over I omega n omega minus EK. And that's the exact Green's function of the resonant level model. This is the self-energy correction two factors of P bar and the propagator of the conduction electron. The 1 over volume comes from the Fourier transform when you go from the local C0 to CK. And you sum over all K. So the intermediate state have arbitrary momentum, the F electron has no momentum. So the K, you prime, all the intermediate states are summed up. Okay. All right, so this is a very easy integral to evaluate. Actually, I should have called it small d of e. That's really what the function is called in the notes. Big D of E is something we're going to reserve later for the many body density of states. This is the single particle density of states. Did I get the sign right? Yeah, okay. So now you can convert this integral to this sum to an integral and write this as I omega minus lambda bar minus P bar squared over V. And this will be integral dE d of E over I omega n minus E. So just the Hilbert transform of the density of states and frequency I omega. Okay. All right, so this, you can certainly evaluate this if you want to do much better. But we're always, we're interested in the regime where the coupling of the impurity to the conduction band is weak. And all of the interesting phenomena are happening in a small window near the Fermi level. So we can just replace this d of E by a constant. There may be some cutoffs over here. And so then we just want to replace d of E just by its imaginary part. And that's just I minus I pi d of 0. So you can just take the imaginary part of this as omega goes to the origin, and then you that gives you delta function, the imaginary part, and then this d of it just comes out. Okay, and the real part we just ignore because it mostly is small and won't be as important. Okay, so the net result is that the Green's function is I omega minus lambda bar. Notation here. Plus I gamma sine of omega. This omega is probably a sine of omega here. Okay. So it's just a constant with the same sign as this term over here. Okay. And that's the promised Lorentzian. So the density of states, rho f of omega, which is m of minus m of gff, omega plus I eta. That just turns out to be 1 over pi gamma over omega minus lambda bar squared plus gamma squared. Where gamma, sorry, I have to tell you what gamma is. That's the most important thing. Gamma is pi times p bar squared times the density of states at the Fermi level. Okay, and this is easy to see. This is just actually exactly Fermi's golden rule. Factor of 2 pi matrix element squared times the density of states. So this is basically the resonant level decaying into the continuum, rather similar to the decay of a nucleus, where an alpha particle goes from a bound state inside the nucleus out to the free space. Here, there's this F electron, which is sitting over here, and then it decays out into the continuum, and the rate is just given by Fermi's golden rule. Okay. All right. So we've gotten the F-Green's function in this model, and that actually already tells us how we're going to solve this. You can now you can see that the integral under this Lorentzian is exactly 1. And so if you want to have mean occupation number 1/2, where there's a lambda bar here, you want to occupy these states and not occupy those. And so this equation right away tells us immediately, this tells us that lambda bar equals 0. That's the solution to that equation, because if you write at the center of the Lorentzian, exactly half the states are occupied. Okay. So the next trick is to then figure out the solution of the other equation, P bar equals this. So that involves determining the off-diagonal Green's function. I think I'm going to skip all the formalism. It's just very simple. These are just summing graphs like this. So let me just write down what the equation turns out to be. Okay, so I'm sorry, I want to get the same notation in the notes. In the notes, I call this A sub F without the pi. Yeah, there's no pi here. Put the pi there. Yeah. That's about right. Okay, all the factors of pi are correct in the notes. So then this equation here, if you just work it out, becomes the following equation. It gives you P bar is JK times P bar minus infinity to infinity d omega over pi AF of omega, the spectral density of the F level, and then you get this in here, F of E omega. These are the Fermi functions, or omega minus E. So that's what this equation becomes when you try to solve it. Okay, so what you see here is a susceptibility, like the Lindhardt function, without any momentum. That's typically what you get when you evaluate a graph like this. You have a C electron here and F electron here, and you evaluate this graph, this bubble. That's what gives you these susceptibilities, and that's essentially what you end up doing when you just work out these Green's function. I'll leave the details of the notes. They're really all the details are spelled out quite explicitly, and hopefully there are no sign errors in there. Okay, this is what you get. So this equation is similar, if you remember back a couple of months ago, to the kind of equation you get for the gap in the BCS solution. There also you had some gap function delta, which was equal to some interaction parameter u, here is jk, and then there was a self-consistent expectation value, which involved tanh functions and so on. Here it involves the convolution of the F density of states with the Lindhardt function at energy omega. There's no momentum here, that's the big difference. You just integrate over all momenta. The conduction electrons, in effect, only come in through their effect on this lifetime. Also, I should emphasize, it's not right to, the word lifetime is kind of loaded, especially in condensed matter physics. These are perfectly well-defined single particle states. They're completely coherent. They're all extended. There's a resonance in the local density of states of order gamma, but there's no actual decoherence. It's not a lifetime in the sense of decoherence. Decoherence requires energy exchange and inelastic scattering. There's none of that here, at least at this mean field level. Okay, so now that's the last thing you have to do is to solve this equation in the low temperature limit for P bar. This will give you P bar as a function of JK. And here, this AF of omega, remember, also involves P bar because AF of omega has this inverse lifetime gamma, or the width of the level, which depends on P bar squared. All right. So the first thing you can do is just cancel this P bar on the left and the right hand side. P bar equals 0 is always a solution, just like the gap equation of superconductivity, but that's always turns out to be the high energy solution. And so you hope that the remaining equation will have a solution no matter how small the value of JK. What could happen, which happens in some cases and will happen later in other models we're going to look at, probably on maybe next lecture, is you can ask what happens to the right hand side as JK goes to 0. So JK is making smaller and smaller and smaller. And if you cancel out P bar, the left hand side becomes 1. Now this is a very small number. So if you want to have any hope of solution as JK goes to 0, this expression here better diverge as JK goes to 0. If it doesn't, you won't have any solution. And the only solution would be P bar equals 0. But in fact, in this case, this expression does diverge. So you're guaranteed to have a solution no matter how small JK is. So this is telling us, in the end, that's the essence of the Kondo effect, really. You have the spin, which is sitting here on its own self, but the moment P bar is non-zero, it becomes like an electron. It's got a width, and it just becomes an extended state with mixes with the Fermi C of the conduction electrons. And that width is just equal to P bar squared. So if P bar was 0, it would mean that the spin remains a spin. It doesn't become an electron, it just remains a spin on its own and would give a Curie susceptibility. But it turns out, for the key really to the solution is the fact that this function has a divergence as P bar goes to 0 or temperature goes to 0. Okay. So we go ahead and cancel it, assuming there will be a solution. So the left-hand side will be 1 over JK, and that's going to be equal to this function. All right, so now that function is relatively easy to evaluate at low temperatures. Again, yeah, so you have to, so this is from some bandwidth. I guess I called it lambda last time, so maybe I call it lambda. Okay. And you go ahead and evaluate this. And what do you get? So first of all, you do this integral very carefully at low temperatures. And this will give you minus 16 to infinity, d omega over pi, omega. This is just an integral of Fermi function, so you can do it. And this turns out to be d of 0. Oops, I forgot a factor of the density. It's somewhere. Yeah, there's a factor of the density of states. It doesn't involve p bar. The p bar is only in here. And then that turns out to have a log divergence, which is the key to everything at 0 temperature. That turns out to be d of 0 of log of mod lambda over omega. We'll see eventually that this log divergence has an origin in the fact that this F state, it just has a single energy. It has no dispersion. That's what leads to this. This is the same log that we saw earlier in the Kondo perturbation. And now this is a Lorentzian times the log, and in the limit where the Lorentzian is very narrow, you can evaluate this integral too. And this turns out to be basically d of 0 density of states and log of lambda over gamma. Okay, so there's our basic equation, and now we've got the basic equation for the Kondo energy. And gamma was pi p bar squared times the density of states. I mean, gamma is a more physical quantity than p. We don't really care about p bar. Gamma is what appears in a response function as the inverse lifetime of this F level. Okay. So now we can solve this for gamma. So gamma, of course, is lambda times exponential minus 1 over d of 0 times jk. So this was exactly the answer we obtained last time using the RG argument. And here it is with all details put in, at least in the notes, all factors of truth done carefully, all integrals done carefully, and then you get that the lifetime of levels is basically of order what we call the Kondo temperature. So there's a characteristic energy scale which determines the dynamics of this impurity. And associated with that, there is also a length scale, C, which is the Fermi velocity divided by the Kondo temperature. And the idea here is that when you go below the Kondo temperature, your local moment, which is just a spin that was free to fluctuate and gives you the Curie stability. When you go below the Kondo temperature, it's no longer a spin. It's kind of dissolved into the continuum. It's become part of the continuum. And it's just another resonant level with the lifetime, which is the Kondo, the inverse of the Kondo temperature. And so effectively what's really happened is that the spin has formed some entangled state to the conduction electron. That whole entangled state has a size of Vf over the Kondo temperature. And if you looked at very low energies, it just looks like an electron, a local resonance of some electronic state with a width of order the Kondo temperature. This is sometimes called the Abrikosov-Soule resonance, and be relevant to photoemission measurements of the electron spectral function in a Kondo system. So, Kondo resonance. So the only difference in the end between the free electron resonant level model and the Kondo resonance is a question of energy scale. In the free electron model, the Kondo resonance is, the resonant level has a lifetime, which is determined by the tunneling matrix element, for the electron to go from the bound state to the continuum. Here also, it seems like there's just an electron there, which goes from the bound state to the continuum, but the lifetime is highly renormalized from any bare coupling. It's given by this exponentially small width, which is exponentially small in JK. I mean, if you were doing perturbation theory, you might think it's out of JK squared or something, but it's actually much, much smaller. Okay, so this mean field theory is very powerful. You can use it to compute all kinds of things. So many of the things I mentioned last time, including the resistivity and the spin susceptibility, and so on, you can work out, and they kind of confirm the physical picture that I presented.
Is this mean field theory a substitute to the Bethe ansatz analysis, or?
This is, well, the Bethe ansatz analysis would be for m equals 2.
Okay, so
This is for large m. Yeah, so it agrees perfectly with the Bethe ansatz analysis. Also, a very nice thing about this is, in general, there could be a numerical factor here, which depends on m in the exponential. It could be different for m equals 2 than opposed to large m. It just turns out that this is the correct numerical factor inside the exponential, even for m equals 2. You know, like in the nonlinear sigma model, you're at n minus 2 in the exponential.
Yeah, but the factor in the exponential can be obtained just from one loop analysis, right? So it's
correct. That's right. That's right. But one loop analysis for m equals 2. So the factor in the exponential, of course, we know the exact factor. Correct. Now we're doing a large m factor. There's no large m calculus. There's no guarantee you'll get the same factor in the exponential. You'll only get the factor valid for m goes to infinity. So, for example, in the O3 nonlinear sigma model in 2 dimensions, that's the case. You get a different factor in the large m limit that you get from n equals 2. Here, it turns out to be much simpler. It's correct. Yeah.
Could you just remind us what's the function f of epsilon?
Oh, sorry. This is just the Fermi function.
Oh,
Or a step function at 0 temperature. So all the chemical potentials have been absorbed, and in going from here to here, I just replace it by a step function. But if you had a finite temperature, then the temperature would also appear as a cutoff.
Subir, is there a Kondo minimum in this case?
A Kondo minimum. Well, the Kondo minimum refers to the resistivity. Is that what you're asking about?
Yes, for the resistivity.
Yeah, so you can compute the resistivity. So that would involve, looking at the conduction electron Green's function and getting the T matrix of the conduction electron Green's function, and then computing the contribution resistivity from that T matrix. What you'll find there is that you get a contribution to the resistivity. I don't know how it scales with TK, but it'll somehow depend on gamma. I don't remember the dependence. So what this will give you is a resistivity that, let's say, is, what is that? Well, you have to look at things as a function of temperature. So you have to determine gamma as a function of temperature, and that would involve solving this equation more carefully. So you have gamma as a function of some temperature, and gamma will increase at some point. I think it goes 1 over the Kondo temperature. I'm sorry, I don't remember. So this will give you, in terms of the contribution to resistivity as a function of temperature, some contribution that goes up to some finite value at the scale of all the Kondo temperature. So this you would get by doing the kind of calculation just outlined, and I'm sorry, I don't remember how delta rho depends on TK. So this is what it will give you, something that goes up as a function of temperature. But now you add to this some phonon contribution, and the sum of those will have a minimum because the phonon contribution has the opposite temperature dependence. That would have some temperature dependence that comes in like this. So you add these two lines and you get a minimum somewhere here.
Because I was just trying to connect it to the RG analysis that you did last time. So is there a sort of a blocking mechanism that you can use in this case to understand how the RG connects to this exact calculation that you've done?
Yeah, good question. I mean, the blocking mechanism is in this Fermi function here. The RG you can think of. One second. So this log here is very much the RG. So you can think of this as the first one loop correction to the value of JK is this term here, but now this whole thing is done self-consistently so that what appears, so what would happen in the RG is when you computed the one loop correction to the Kondo coupling, instead of getting gamma, you get the external frequency omega. And this calculation just makes the whole RG self-consistent by replacing the external frequency by the Kondo scale itself. Okay. I mean, this one loop graph is essentially the kind of graph we had last time. We had this kind of graph here for the RG, remember? Sorry, can you see that? You had some spin here and a C electron there. And so now you can replace the spin by an F. And this is the one loop graph of F and C. And that's exactly what gives you this Fermi function over here.
And where does the phonon contribution come in the RG?
It doesn't at all. No. The phonon is just for the resistivity. We're just looking at this model here, and there's no phonons. It's just conduction electrons coupled to a spin. And so this particular model will just give you the white line of the resistivity. It'll give you some resistivity that goes up a bit as you go to low temperatures.
But in the RG analysis, you do get the minimum. So I'm just wondering.
No, you don't. You don't. The RG analysis would just give you the initial rise of this.
I see.
Kondo's calculation will just give you this thing going up. This large M calculation in principle, allows you to go all the way down to 0 temperature. So Kondo would just give you a little rise. The large M will give it all the way down to 0 temperature. And then you add the phonon, which is completely external to this calculation. The sum of these two will have a minimum.
Thank you.
Yeah, there's no phonons here at all. The RG just gives you the initial rise of this. And the RG tells you basically JK goes to JK plus JK squared times log of lambda over temperature, say. That JK squared log lambda over temperature comes from this kind of graph here we discussed last time. And what we're effectively doing here is by replacing this temperature by gamma is essentially summing an infinite number of these. And which is kind of what you see from these lines here in the resonant level more. Okay.
Yeah.
So in this case, all the details are definitely in the notes, and not of the resistivity, but everything else. And so really, hopefully I'm getting the point across clearly. And if you look at the notes, hopefully it'll all be clear. Any other questions?
Oh, excuse me, Subir.
Yes.
If I formulate in terms of some continuum field theory, would some version of Gross-Navier or Gross-Navier-Yukawa will be able to capture what you described, or it's not quite?
Well, the large M analysis has some similarity to the Gross-Navier model, actually, not the Gross-Navier-Yukawa. But one important difference, if you look at the original Hamiltonian, has to do with conservation of momentum. So the Gross-Navier model, in fact, I'm going to write down something like the Gross-Navier model in a minute, will have the F and the C coupling at all sites, not just at the origin. The C is only at one site. Whereas the C at one site is coupling to the F at the local site, whereas this term, the C, is allowed to move between site and site. So it's not like a bulk Gross-Navier model, it's more like a boundary model. So the C, maybe I'll say a few words about that, since others have also asked. And apologies to those who are not versed in conformal field theory. So one way you can think about this problem is the following. So there is a very beautiful reformulation of all this using the conformal field theory language. So let me just say a few words about it. I won't really use it, but it gives essentially the same results. So the way you think about it is you have this Fermi surface of conduction electrons. So that's just the C particles. So the first thing you do is you just only look at the radial motion in S wave. So you take only S wave particles and you just look at the radial motion. So you can replace the whole three-dimensional Fermi C by a one-dimensional Fermi C because you're only looking at the S wave channel. So you have then, roughly speaking, the S wave channel, you have a line with an impurity spin sitting here, and you have the conduction electrons coming in and getting scattered back. And you can think of this direction as a radial direction, which stops at the origin. So you go to spherical coordinates, and you have incoming waves, spherical waves, and outgoing spherical waves, and they scatter up the spin at the origin. That's effectively the problem you solve. When we did the sum over K and computed the lifetime, that essentially had no angular summation, and it's just dominated by the density of states, so that's the problem you're solving. So then what Affleck pointed out was that you could unfold this problem where you can, rather than think of in half space, a particle going back and forth at the spin at the boundary, maybe this was Cardy had known this earlier, you can take this other problem and put it over here. So then you get a problem which is a chiral conformal field theory coupling to a spin degree of freedom at the origin. And that picture then leads to very powerful techniques for solving it. Although in this case, you don't learn much more than you already knew because it also flows to strong coupling. But in the multi-channel case where the spin goes to some critical fixed point, then you can use the powerful techniques of boundary conformal field theory to really make some exact statements about the multi-channel Kondo problem, which you couldn't in any of the previous methods. Well, the Bethe ansatz had also solved that case also earlier by Nathan Andre. Anyway, so that's the connection.
Sorry to interrupt. Multi-channel means the spin has spin more than half. The spin is more than spin.
No, it's really that the conduction electrons have extra labels.
Spin still a spin one half?
Yeah, it's equal to spin a half. So it's a problem where the conduction electron has another flavor. So you could take exactly this problem and just put a flavor, P flavors of conduction electrons. You could also make the spin larger. And that whole class of problems and many other interesting critical points.
I will make a comment for the string theorists.
Yes, please go ahead.
The multi-channel Kondo model has some interesting geometric interpretation in terms of difference on S3 and the S2 WCW model, and fuzzy spheres and so on.
Okay, thank you, Juan. Any other questions? And now we're going to the next topic is the Kondo lattice model. So this is about all I want to say for the Kondo impurity model. This is a very good picture to keep in mind to understand what's going on. It's just some kind of Lorentzian level of it's an electronic level, and otherwise it's just free electrons. And all the complicated interaction effects are in the temperature dependence of the width of this level. Okay, and the spin has effectively become part of the Fermi C. All right, so this theme of the spin becoming a fermion will be very much part of our discussion of the Kondo lattice model now. Of course, the spin started life in the Anderson model as an electron, but we view that as not an appropriate description because the Anderson model has a very strong coupling, this UD on the D side, which we really want to send to infinity. And then we want to look at the Kondo model, which is really the model of spins coupled to conduction back. All right, so let me go to the Kondo lattice model. And as you'll see, now you see the power of the large N method because I have to make very small changes to everything on this board to just write down the saddle point equations anyway. So the Kondo model is, first of all, I do a sum over I here. K over N. I put an I on each of these. I, All right, that's it. And so I'm putting a spin in every site. So each conduction site of the conduction electron has a spin at its disposal.
But the spins are not mobile.
Yes, yes. I'm going to keep them immobile, but later on, but probably not today, we can add direct exchange interaction between them. But they're not going to move. The electrons, these are just still spin-offs. They will remain spin-offs. All right, so that's the Kondo lattice model, and it's of great importance to various intermetallic compounds. They have very complicated formulas, something like uranium, beryllium-13, where these are the uranium ions, the Fs, and the conduction electron, the electrons for the beryllium ions. So there's a lot of complicated band structure and spin-orbit couplings and many complicated things that I don't understand. But fortunately, much of the basic physics can be understood in this highly simplified model, where you just have one spin for each conduction electron, and you want to determine the phases of this model. Okay. All right, so everyone understand what the model is. The model now has complete translational symmetry. So momentum will be a good quantum number, unlike what we talked about before. It doesn't map onto any boundary, conformal field theory, or anything like that. It's really a model of a strongly interacting metal in d spatial dimensions. Okay. Okay, so that's the Kondo lattice model here. So the questions, what are the questions we want to ask? Well, this is a system that's, well, let's look at the limit where jk is 0. When jk is 0, then you have a bunch of spins, which are left to their own, will just give a big Curie susceptibility. And then you have a bunch of conduction electrons, which will form a Fermi surface. Okay, so, and if you're at high enough temperatures, the density of conduction electron, which I'll call C, density will be rho C, sorry. So at high T, what do you expect? Well, you have a bunch of spins which will do their own thing, give you Curie susceptibility, and the conduction electrons, you're still below the Fermi energy of the conduction electrons, but much above the Kondo exchange, which is a much smaller number. The conduction electron will form a Fermi surface of size rho C. So you would have just take a density rho C and compute that to the size of the Fermi surface. And this is what we call a small Fermi surface. Of course, this is a very qualitative statement because the concept of a Fermi surface is only precise at 0 temperature. But okay, at some there, there's some intermediate temperature range where you're much above the Kondo temperature, but much below or much above JK, shall we say, but much below the Fermi energy, where the Fermi surface is reasonably sharp. You can see it in an experiment, and so that's only counts the density of the conduction electrons. So the question really is, what happens as you go to low temperature? It will, in general, unless you're at some very special densities, it will remain a metal. So you go to metallic state at sort of low temperature. And the question you have to ask is, what kind of metal? So what are things that characterize a metal? Well, first of all, does it have quasi-particles? In fact, you're not going to do anything that drastic today. So yeah, it will have quasi-particles. Then if you have quasi-particles, the other question is, what is the size of the Fermi surface? And what are the effective mass of the quasi-particles? So these are the questions we want to know. And in the simplest theory that I'll discuss today, in the heavy Fermi liquid, what you find is that the Fermi surface is large. And the effective mass of the quasi-particles is also very large. It's 1 over the Kondo temperature of a single impurity. That's the result I want to show by the end of this lecture. So that state of matter is often called the heavy Fermi liquid, because the mass of the quasi-particles can be quite large, 1,000 times the bare mass of an electron, and the largeness of the mass of the quasi-particles is very much connected to the smallness of the Kondo temperature in the impurity model. So that's what I'll talk about today. And if time thinks right, I'll explain to you the basic structure of the heavy Fermi liquid. And then next time, we'll start to think about this more carefully and ask questions. Could there be another phase of matter where you don't count the spins inside the Fermi surface? Okay, but just very loosely speaking, this was definitely the understanding for a long time, and also confirmed in many, many experiments. There's kind of two reasons for expecting, two ways to understand why you would expect the spins to become part of the Fermi surface. One is you go back to the Anderson model. The Anderson model has large interactions, but let's do perturbation theory in interactions. Then at zero interaction, the spins are actually electrons. Double occupancy is allowed and everything. And that will definitely have a large Fermi surface, but you think of the spins as electrons. But then you also know from the Lattice theorem, which I will also discuss next time, that to all orders in perturbation theory in this U, and some claim sometimes incorrectly, exactly, the Fermi surface doesn't change no matter how large U is. So then you would conclude, yeah, if the Fermi surface doesn't change, the size of the Fermi surface doesn't change, if you turn up the interactions, you should have a large Fermi surface. So that's one point of view. But it's a bit unsatisfactory because, it really requires extrapolating from U equals 0 to U equals infinity, always very dangerous. A more satisfactory argument to me is by analogy of the Kondo effect. So this model, as written, has no large energy scales other than the constraint, okay? But there's no large energy scales. And what we learned for a single model was that the spin effect below the Kondo temperature just became an electron. It had a Kondo resonance and it dissolved into the Fermi sea. So maybe that's exactly what's going to happen here. All of these spins are going to dissolve into the Fermi sea, and the net effect is that this thing is going to become larger. So that's what I'm going to show you now, how that happens. All right, any questions on that general overview? So let's just now fix the large M theory. This is also easy to fix. That's lambda bar, sum on I, Fi alpha, and P bar is to the constant, Fi alpha, Ci, there's a sum on I on this whole thing. Let me write it like this. I, bar. This is still true. You take any side here, if I no sum on I. And this is also true. Take the local expectation value, and this is P bar. That's it. Just by changing a few indices, it's exactly the same large N theory. But one very important difference now, momentum is conserved. So the graphs you're going to look at are going to be very similar, but they're going to have a rather different form because of the conservation of momentum. Okay, any questions there? So now our task is to solve these equations. Okay. And everything I said will come out from the solution of those equations. So now it's just a purely technical problem of solving these equations. In fact, it's probably a little easier to solve them graphically than analytically, but all the details are definitely in the notes. Okay, so now we're not dealing with a resonant level model because there is no impurity, there is perfect conservation of momentum, and so we're just dealing with some band structure. So you just make a Fourier transform into the momentum space, and then your Green's functions are extremely simple because the mean field Hamiltonian is a free fermion Hamiltonian. All right. So you can write down the bare Green's function of the F electron, which is I omega n minus lambda bar. This will be now, it's in fact momentum independent. This is not the actual Green's function. This will be k n omega. Okay. Then what about the conduction electron Green's function? Well, let's get it to all orders. Gc of k n omega will be what? Well, it'll be very similar to what we had before, but there's the bare Green's function, I omega minus ek minus p bar squared over I omega minus lambda bar. That's it. So this is just some of these graphs again. C, F, C, but now it's the same momentum in every line, and so on. So you sum all of those graphs and you just get this very simple expression for the Green's function. And now you just have to take this Green's function. Let's also write down GCF of k n omega, because we're going to need GCF of acid. Well, let's see. Yeah, we're also going to need the fully renormalized GF to solve this equation. Now it won't be as simple. We won't just put lambda bar equal to 0. We'll have to worry about what lambda bar is. So let me just write down all the Green's functions. That's pre-fermion. So the band theory. So GFC, minus P bar, I omega minus lambda bar, times GC, and GFF, the full Green's function, GFF, is okay. These two equations are quite easy to understand. So here you have a bare F. It can be just that, plus it can be a bare F times the fully normalized Green's function, so C, and then another F. So that pretty much, so this must be squared. Okay, or you can just diagonalize a 2 by 2 matrix. Many ways of doing this. But I'm just doing it in a way that makes the connection to the impurity model much more explicit. All right, so these are, you have all the Green's functions, you can take this Green's function, insert them into these two equations and solve them. All right, so let's see what we get. Okay. All right. So again, there's a bit of messy algebra, and I refer you to the notes for fairly explicit details on the algebra. All right, so let's actually look at this. Look at the what is this? Where are the poles of the Green's function? But all of them have poles at the same location. They come at the solutions of this equation, and that's going to give us the band structure. So the poles of GC are at EK plus minus. Where EK plus minus is the solution of a quadratic equation. It's just EK plus minus EK plus EK plus minus lambda bar minus P bar squared equals 0. Or another way to see this, which you could have already seen from there, these are just the eigenvalues of the matrix, EK lambda bar minus P bar. Eigenvalue of this. Well, the reason everything is so simple is because of momentum conservation. It's just a 2 by 2 matrix for each momentum K. All right, so let's solve this graphically and try to think about, how to solve these two equations. So now in the solution, I will anticipate, which we will verify, that P bar is going to be very small. In fact, it's going to be pretty much the same value of P bar that we found for the impurity model. So let's just look at the structure of what happens when P bar is very small. Okay. So I'll do that over here. So important to get this figure exactly right. All right. So I'm going to plot So this is where, it's kind of messy solid state physics, not informal field theory, but it's still very interesting. So here's momentum K along some direction. And here's the energy of the quasi-particles, could be F or C. Okay, to begin with, what's the band structure at P bar equals 0? So let's for now keep P bar equals 0. Well, then the eigenvalues are very simple, it's just EK and lambda bar. Okay, so now I will draw EK. Maybe it's some function like this. And there's lambda bar, which is good. All right, so. And this will be 0 here. Okay, so this are called KF star. That's the Fermi wave vector of the small Fermi surface. It's a small Fermi surface. Okay. And these states are going to be filled. Okay. So this is EK. Sorry. Then what about this object? So in this limit where P is 0, I still have to satisfy this equation with constant energy. Well, that's kind of a limiting case. If you work at 0 temperature, you get nonsense. But let's say you're some small finite temperature. So a small finite temperature, the expectation will have F dagger F. On any side would be just the Fermi function, e to the lambda bar over t plus 1. And now you notice here, when you put lambda bar equals 0, this is 1/2. So lambda bar will be just 0. And that will allow you at finite temperature to get exactly half filling. So lambda bar will also be right here. So this is the F dispersion. This is the F electron. And that's lambda bar equals 0. Okay. And this KF star corresponds to a density of rho C. Okay. All right, so now we turn on a non-zero P bar, and let's assume P bar is small. Well, what's going to happen now in this theory? So these bands are going to mix, and they're going to mix something like this. And this would be, there'll be the other band, which will come in flat and then go up like this. Okay, so this we're going to call, this is EK plus, and this is EK minus. Okay, so what do we have to do? We fix the density of the conduction electron at rho C. The density of the F electrons is 1 per site, so or 1/2 per spin. And so we now have to fill up, these are free electrons. We just have to fill up 1 plus rho C states. Okay, so I'm going to assume here rho C, the conduction electron density, is less than 1/2. If it isn't less than 1/2, well, things change a bit, but not too much. And here, the assumption is this is per spin. And if you fill up all states from here to there, from 0 to pi, that will give you a density of 1. So This is after integrating all the angular direction. So if you fill up every state up to there, you get a density of 1. Okay, that would be an insulator if you had that happening. But here rho c is 1 plus a half, less than a half. The total density is 1 plus rho c. Sorry, I have to remember, was rho c per spin or not per spin? Excuse me for a minute. Okay, sorry, yeah, I'm doing it with spin included. So rho c is less than 1, and the total number of electrons you can fill up to here is 2, not 1, because I'm counting spin. Excuse me. Okay. So rho c is less than 1, so 1 plus rho c is less than 2. This means I can save the day by just filling Ek minus. I don't need to fill Ek plus. I have enough states on this band to satisfy the constraint on the density of the C electrons and the density of the F electrons. So basically, I'm going to be sitting somewhere here at my actual KF. This will be my true KF. And this will accommodate the difference between these two will be density of 1 for total, or 1/2 per spin. So KF star will move from here to there, and you get a Fermi surface out here. So this is the large Fermi surface. And this is for P bar not equal to 0. Okay, so that's the prediction of the large N theory. As long as P bar is non-zero, the F electrons do dissolve into the Fermi C, and the size of your Fermi surface moves up to here.
It seems you could describe it by saying that the conduction electrons dropped into the unfilled states of F, of the Fs.
You could say that, yeah, right, because you're only occupying the lower band, yeah. But another way to say it is that the F electrons now acquire a dispersion, but by the mixing. Once you diagonalize this matrix, the F electrons didn't have any dispersion, but once you diagonalize the matrix, these new eigenvalues do have a dispersion. Okay.
So here it was important that the M was 2 or not for the minus.
Yes, then the counting is for M equals 2, right? But it works. I mean, this will have to be changed to M over 2 and so on. Yeah, I have put M equals 2 in the counting, but it'll work for any value of M. I just haven't put the
If you had the chance for so that I understand. So if you had, let's say, larger value of M, then each spin counts as roughly M minus 1 electrons. Or?
No, so the constraint is M over 2. There's a 1 over M there. So each spin counts as M over 2 electrons.
Oh.
Yeah, or 1 electron. So that's the 1 here. So this will be replaced by M over 2. And rho c would have to be also less than M over 2. And you would have M electrons that you could occupy in the full Brodel zone. But I'm not going to try to fix that. I might make some errors. That this is all for M equals 2. Okay, so we're almost there. So we've got a large Fermi surface. The next question is, do we have a very heavy mass? Okay, and now you can see just from this picture why the mass should be very heavy. This F band was completely flat, that's the red line, and it acquired a little bit of dispersion, but it has a lot of dispersion here. The curvature is very large, but once you get out here, it has hardly any dispersion because it's very far away from the mixing point. And it's forced to go out there by the counting of the total number of electrons. So it has to go out there. And this line is essentially flat. And because it's very flat, it tells us that the Fermi velocity is very small. So VF is extremely small, or M star is large. In fact, roughly, if you just estimate from the dispersion, let's see, sorry, VF goes as basically P bar squared, and the F star goes 1 over P bar squared. Okay, more precise expressions are in the notes. Yeah. All right, so this is the heavy quasi-particles, provided P bar is small. Okay, so finally we have to determine P bar. That's where it all comes down to. And that involves solving this equation. So again, that's easy to work out. I gave you an expression for GFC, which I erased. Just use GFC to evaluate this at 0 temperature. It's easy to do. In fact, even easier than the Kondo impurity problem, because there's no lifetimes to worry about. No Lorentzians to integrate over. And what do you get? Okay, so I'll write down the equation for P bar. So as we'll see, it's not exactly the, so P bar at 0 temperature, T equals 0. Equation for P bar turns out to be P bar over JK. Looking very similar to the Kondo impurity problem. P bar over V, sum on K of occupied levels, which are assumed to be only in the lower band, over square root of epsilon K minus lambda bar whole squared is 4 P bar. Now it's looking even more like the BCS expression. There you had a gap, and there was a gap on the right-hand side, and some interaction parameter, which we have put down there. And then there was a tanh function, so that's a little bit different. And there was square root of some E squared plus delta squared. So this is very much like the BCS gap equation. There's no gap here. Well, sorry, there is a gap between EK plus and EK minus, very tiny, but your Fermi level is in the lower band. So then you have heavy Fermi liquid. Now, if it just so turns out that rho C was exactly 1, then this band will be fully filled, the other band will be fully empty, and you get what's called a Kondo insulator. And there are also many materials which are in that class. Just like the Kondo, the heavy Fermi liquid, what distinguishes a Kondo insulator from a regular insulator like silicon or diamond is that the gap is much, much smaller than you would think. It's entirely from interaction, and as you'll see, it's exponentially small. So P bar is the key quantity. And again, the same issues apply here. As JK goes to 0, so the left-hand side becomes large, is there a solution with a non-zero P bar? And again, the answer is yes, because as you can see here, this expression also has a log divergence. As P bar goes to 0, there's a log here associated with the integral of EK. EK is over here. EK minus lambda bar is also somewhere over here. So you get, there's a 0 from here that you have to worry about when you do the integral over K, and that gives you a log divergence. Again, the details are very much in the notes. All right, so in fact, there always is a solution. And if you try to trace it back, and this is what we're going to do probably next time, if you try to trace it back to where this log is coming from, it's related to the fact that the F band was totally flat to begin with. Once the F band has some own dispersion, then the log divergence disappears, and there can be solution with P bar equals 0. Those are much more exotic, and that will be the topic of some discussion soon. All right, for now, we just go ahead and cancel this, assume there's a solution on both the left and the right hand side. And if you solve this, you do the integral in the appropriate limit. Skip the algebra. On the right hand side becomes 1 over jk twice the density of states at the Fermi level of the conduction electrons and log of lambda over p bar, which is exactly the expression for the Kondo problem. I guess I had a lambda squared there. Okay, so this gives us basically p bar squared. It goes as the Kondo temperature of a single ion. And that tells us that the effective mass is also the inverse of the Kondo temperature. It can be huge. Okay, so that's the summary of the basic structure of the theory. It's remarkably simple, but actually hides a lot of very deep physics, and also amazingly, for something so non-trivial, agrees with many, many experiments. So if you just think about it, this is quite a remarkable statement. You have conduction electrons, those are electrons interacting with some spins. Now, of course, in the physical material, these spins are made up of electrons themselves. But in principle, these could be qubits in a quantum computer. You could have superconducting qubits, two-level systems, coupled to some conduction electron in a metal. And the claim is that those superconducting qubits would become fermions, would become part of the Fermi surface. That's what the claim is here. The spins have become fermions, and in a way that is rather shocking because it's less shocking in the way we presented it because we started the model which had electrons in it. But if you forget about that the spins came from electrons, they could come from anything. It could even have been, made up of superconducting qubits or nuclei or anything. Then the statement is that at low enough temperatures, lower than this Kondo temperature. Now, of course, in many situations, this Kondo temperature is exponentially small, which is why you wouldn't see this effect. I don't think it'd be that easy to see with superconducting qubits because the couplings are not large enough. But in principle, in the right conditions, you would have then this state of matter where these qubits became fermions and the Fermi surface moved up and counted not just the number of electrons as it did up to here, but all the qubits. These fermions here at the Fermi surface, they're just ordinary particles. They carry charge and they carry spin a half. And there's quite a lot of them because the Fermi surface is large, effectively. They're very heavy. And there's many more than you would have naively guessed just by counting electrons. And that's really the impact of the Kondo effect. Shows you how non-trivial the Kondo effect is and how it literally does turn spins into electrons using this large Fermi surface. So from that, yes.
Well, to claim this would happen, you have to assume this effect dominates over spin-spin interactions.
Exactly. Right. So that is precisely the next topic I'm going to turn to. There can be another situation, which, as you said, from one point of view, is the more natural situation, where the spins don't turn into electrons. And that's what we'll talk about. That leads to a state we sometimes call the fractionalized Fermi liquid, where this high temperature state survives all the way down to zero temperature. But when you take this down to very zero temperature, then the question becomes, what do the spins do? You have, one spin per site, and they've got to form some state of matter. Now, what do spins do when you lower the temperature? Well, we saw all these constraints on spin systems in our discussion on spin liquids. In particular, there's an odd number of electrons per site. Then there is no trivial state. The spins have to have some emergent gauge fields. They have to have some kind of spin liquid state with some fractionalization. Without that, this state is not going to survive down to low temperature. They could have a broken symmetry, but then that's a whole different state, which is quite natural and easy to understand. So really, for this state to survive down to very low temperature without any further broken symmetry, you need something rather exotic to happen because of the constraints that come on the structure of spin liquids. And these are intimately connected, as this discussion makes clear, to the constraints of the Lattice theorem. And those are really two sides of the same coin, and that's really what I want to talk about next. The Lattice theorem, and also say a little bit about its connection to emergent gauge fields and various constraints on spin liquids that we've already encountered. What's happened here is that there's no spin liquid. All the gauge fields in effect disappear, and you just get a Fermi liquid, and the spins become ordinary fermions. So depending on your point of view, that's amazing or completely expected. It is what's observed, though, mostly.
So what's observed is the big Fermi surface is observed in experiment.
Yes, yeah.
And how about the heavy mass?
It depends on the material, but it could be from 5 to 1,000.
But many of it's observed.
Yeah, the effective masses are very large. Effective masses are seen, right? Yeah. So it's in various heavy fermion compounds, also less heavy compounds like what I call the 115 compound, cerium, cobalt, indium 5, and so on. But there also have been a number of observations where it is not seen. Those are the most mysterious, and they're not yet understood. And they all involve trying to understand, what happens when the Kondo effect doesn't win. So, what's happened here is the Kondo effect won, the spins became fermions, and you got a big Fermi surface. So that leads to what's called the Kondo breakdown problem sometimes. What happens if there is no Kondo, if the Kondo effect doesn't win? Then something interesting must happen, something exotic, and we'll turn to that. But before I turn to that, I do want to now go back to a topic I skipped, which is the Lattice theorem, which is, how rigid and how is the fact that the Fermi surface must count all electrons, and when does it count the spins, and when it doesn't count the spins. These are all things we want to talk about. Okay. Basically, the rule is that, as we find, if you have some emergent gauge field, if you have some fractionalization, then you can violate the Lattice theorem. But if you don't, if all gauge fields are essentially Higgs out, then you must obey the Lattice theorem. That's the modern understanding and topics I've worked on a lot over the last few years.
In this case, could you say there was a small Fermi surface and then there was some other Fermi surface, which was the one for the red things that was kind of trivial because all the energy levels were.
Well, if you hear, so if you think as a function of temperature, then the concept of a Fermi surface is only approximately defined at finite temperature. So this is kind of has some width, and as you lower the temperature, this thing just moves from here to there, but it's not very sharp. There's no sharp phase transition as a function of temperature between the red line and the green lines. If you lower the temperature, the question I want to ask is: suppose I'm at 0 temperature and I lower JK. Then there has to be a phase transition between this Fermi surface and this Fermi surface, if such a state is possible. And that phase transition is always a phase transition that involves gauge fields. It's some kind of Higgs transition in the gauge theory. We'll get some idea of that next time. But as a function of temperature, mean field theory might give you a jump, a first order jump from here to there, but that's just mean field. It'll smooth out once you correct it. There is nothing sharp about the Fermi surface or the Lattice theorem at finite temperature. It's only a sharp constraint at 0 temperature. All right, if there's no more questions, this is a good point to stop. I got exactly where I wanted to get to. And the last lecture from this hall will be about the Lattice theorem and its possible breakdown on Wednesday.
How much help is there to observe ordering of nuclear spins in insulators?
I don't know, not much. I think the coupling between nuclear spins and the hyperfine exchange coupling is quite a bit smaller, only a few Kelvin.
A few Kelvin wouldn't be that bad.
Well, it has to go up in the exponential, remember,
Oh, no,
e to the
sorry.
minus 1 over rho.
Well, I wasn't trying to observe a Kondo. How about something more similar like Heisenberg spin order? Any simple phase of spins where the nuclear spins do something interesting.
Oh, that they do with electrons. That's what I'm going to talk about. With electron, if the spins are electrons,
No,
then there are certainly spin exchange couplings between them.
I know. I was asking about whether there's any hope for nuclear spins in insulators. Let's say.
Well, so there you're competing with the dipole interaction between the nuclear spins, which I think they dominate.
Oh, I wanted to ask whether the ordering that produces is reasonable. That's what I was trying to ask.
Yeah.
I wasn't asking about getting.
Yeah, I'm not aware of it. I don't think it's ever been observed. I mean, you're talking about experiments that have to go down to microkelvin.
Yes.
Yeah, those are very hard, but I think those are hard enough that people tend to just focus on insulators with nuclear spins. It'd be interesting to put them in models. Yeah.
Indeed, I was, well,
Mhm.
I might be asking about something that's not novel, but I was thinking about insulators as the easiest case, simplest case.
Well, if you have insulators, then you don't have to worry about the.
Not the things
Kondo
you told
effect.
us today, but the things you told us a month or two ago.
Oh, you can spin liquids of insulating. Yeah, I mean that's possible. I mean, with helium-3, there's there's an insulator at pressure, and helium-3 films. People take films of helium-3, and yeah, there are indications you get a spin liquid there. Yeah, it was a very hard experiment, but people have talked about that.
Okay,
Okay.
thank you.
Sure. Yeah.